Lothar, if you have
Yeah.
time, sometime just visit his lab. I
Oh,
was really blown away. His lab is
uh-huh.
so impressive, extremely impressive.
Yeah, that's very neat. Yeah.
Yes.
So Michael, you are mute. Yep. Yep.
All right, can you hear me now?
Yeah, I can hear you.
All right. Let's see. Okay, can everyone still hear me okay?
Yep.
All right, excellent. All right, thank you everyone for joining. My name is Michael Molina. I'm with the Southern Plains Transportation Center in the Oklahoma Transportation Library. We appreciate everyone logging in and joining this webinar. I'd like to talk about a few housekeeping rules before we begin first. Please, during the presentation, make sure you are muted and your video screen is turned off out of respect for the speaker so we can focus on him and his presentation. After the presentation, we'll have about 20 minutes for a question and answer. You can type your question in the chat or raise your hand and ask a question vocally. We will be providing 1 hour of PDHs for anyone that needs it, and we'll be sending those by email probably within the next week or so. And if anyone has any topic ideas they'd like to suggest for the next presentation, let us know and we can take that under advisement. And we will also be sending out a survey afterwards so you can provide any comments or feedback that you would like to for this presentation. Please do take the time for the survey. That always helps us deliver on our quality next time. So without further ado, I'd like to provide a brief introduction and then I'll turn it over to Dr. Singh. So Dr. Dharamveer Singh is a professor at the Department of Civil Engineering at the Indian Institute of Technology in Bombay, India. Professor Singh's field of specialization is in pavement engineering, focusing on recycling, stabilization, new and innovative technology for road construction, pavement design, and maintenance and preservation of pavements, and forensic investigation. Professor Singh is closely associated with industry and highway fraternity on various fronts, including pavement design, construction, training, and implementation of new technologies. So without further ado, I'd like to turn it over to Dr. Singh.
Okay. Yeah, thank you, Michael. Let me share my presentation here. Can you see that presentation?
Yes, perfect.
Okay, I will turn off my video in case, maybe some issue comes up in between. So you just, yeah, is that all right?
Yeah, that looks good.
Okay. So first of all, a very good morning to all those who are joining from US, and I have many friends joining from India as well, and maybe other part of the world. So greetings to all of you. And this presentation is possible because of the invitation I received from Dr. Jaman on behalf of SPTC, and which is conducting webinar series almost every month. And this particular presentation is going to talk about something different. You're going to see the martial RT and how this idea came up and what exactly we have done to understand this particular simple test, which can help us to evaluate the rutting resistance. So Michael, you just hint me in between the times. So I have just like maybe around 50 minutes or so to complete that.
Correct. Yeah, that'll work perfectly.
Yeah. So first of all, let me acknowledge SPTC. Those invited me for this particular presentations, and thanks to Dr. Jaman, who is my mentor, guide, and the kind of everlasting support and motivations for providing the the professional ethical training to start the career on the right path. And of course, thanks to all my students, those who graduated and those who are working right now, PhD, MTech, masters, and interns. They have really helped me to continue this exciting journey so far. And also, my friends from India, those who have joined, and maybe other part of the world as well. And thanks to IIT Bombay for all the support that I have received so far. So, by the way, this particular work is already been published. If you are interested to learn more about this particular work, this paper has been published in IGPE. Recently, it was published in 2023, sometimes in October or so. And if you're interested to know more about this particular work, and this work was done by one of my PhD students, Mr. Vamsi Krishna, who is also here, who is attending this webinar. And in case we have very difficult questions to ask, I will ask him to, like step in to save myself. So let's start with, I will go very slow because we have all kind of participants here. So I will just try to build up the base of the foundation, what exactly is happening and how we are proceeding in this particular direction. So this is flexible payment, or you can say asphaltic payment, or you can say the bituminous payment. In India, we call it a bituminous payment. And if you see the composition, very simple composition that I'm showing you, maybe there can be n number of combinations are possible for this particular payment. But let's try to understand the simple combination, which is subgrade, and then you have the aggregate layers, then you have the asphalt layers. This is how things look like actually. Once it is constructed, once you blend aggregates and binders together, and this is how the asphalt mix or bitumen mix look like. In India, we usually call it bitumen, and some other part of the world, in fact, in US, they call it asphalt. So we call it bitumen mix. And once it is mixed up and you lay it down in the field, and this is how things look like actually. So this is the flexible payment, this is the asphaltic payment, or you can say this is the bituminous payment actually. So if you see different kind of gradations, the reason I'm presenting that because the mix or the asphalt mix can composed of different kind of gradations. For example, if you see these particular photographs, you see the well graded here, and you see the gap graded number B, and you see the open graded number C. So these are the different typically used the aggregate gradations all over the world actually. And if you see the dense graded and well graded, and in India we call it bituminous concrete. In fact, both are the dense graded or both are the well graded. And if you talk about the gap graded, which is SMA, and which is also being used in some part of India right now, and on mega projects, we have been using this SMA, which is gap graded. Of course, the open graded, you can think about open graded friction cores. So this is how the gradation look like. And based on these gradations, you may have different kind of mixes, which is going to lay down in the field actually. So remember those kind of typical basic fundamental definitions of different kind of gradations that we have. And if you I'm just showing you the Indian conditions, what are the different mixes, but similar things are also applicable in other part of the world. For example, if I say, let's say, for example, bituminous concrete, which is used in the top layer, and if you see the NMES, which is 19 mm, and then we have 26.5, then we have 37.5, the bigger size of aggregate, the smaller size, much smaller, and this is the smaller size actually. So these are the typical well graded or dense graded mix that we have in India, which is starting from nominal maximum aggregate size 37.5, then 26.5, then 19 and 13.2. Usually this kind of mix is used for the surface course, and this is the binder course, and then they can go for the base course actually. We do have SMA as well, which is stone matrix asphalt. Again, there are two typical gradations that we have. One is NMAS 13.2. Another is 19 mm. And then, of course, we have the gap graded rubberized mix, which is not being used widely in India right now. But yes, we have this particular mix as well. So we have typically 7 different mixes, which is being used in India and different depending upon the traffic and climatic conditions. And if you see the type of the binders or type of the mixes or type of the asphalt we have in India and of course in other part of the world as well. We have unmodified binders, which is there is no modification in that. And we have the modified binder, which has the modification in terms of you can have the polymer modifications, you may have the rubber modifications. And in the polymer modification also, you may have the elastomer and plastomers, this kind of typical, the polymers are there. And in the rubber modified, you may have the crumb rubber. And in some part of India, we have the natural rubber as well. So these are the different kind of the asphalt binders or the bitumen that we have. Unmodified binder comes from the refinery, and modified binder is being produced by some of the agencies. They just modify the binders with SBS modifier or plastomers or any other kind of things actually. So if you see the total combinations, we have the different gradations, 7 gradations we have, different gradation, and we have different types of binders. So there are multiple combinations that you can think about actually. For the base coats, for the intermediate coats, for the surface coats, for the traffic conditions, climatic conditions. If you see the recent things, what is happening, not only in India, but other part of the world as well, the loading conditions, the traffic loading conditions is quite intense actually nowadays. In fact, if you see the typical highways of India, you may see the traffic may go as high as 100 e-cells actually, million e-cells. You may go 100 million e-cells actually, maybe more than that sometimes. And the loading conditions are quite excessive. You cannot really control the overloading sometimes on the Indian highways. And in fact, that is the really worry, that how do you really design the pavement and how do you really select the mixes, what kind of composition you have to select, which can really help us to mitigate the distresses. And also you see a lot of temperature change. Its temperature is really aggressively moving higher side, and we do have the challenges as a highway engineer, that how do we design the system which can sustain both temperature and climatic conditions together actually. And one thing just I would like to mention, which is very, very important, and all these fundamentals, what we are talking about, the rutting and all, and in fact, this presentation talks about the rutting only. The shear strength of the mixes is quite important. And there is a lot of work has been done in this area, that how do I really understand what exactly the shear strength of the asphalt mixes. And this is very typical Moore column failure theory. If you think about that, the cohesion comes from the bitumen property. What kind of bitumen do you have? Whether it is polymer modified binders, whether it is unmodified, whether it is some different kind of modifications. So shear strength is quite important. When the load comes on top of the asphalt mix, so what kind of strength or what kind of shear behavior that mix is going to have. And this phi comes from the aggregate interlock, how good your aggregates getting interlocked, what kind of shape, what kind of texture, angularity, sphericity, and what kind of stability they are going to provide. So altogether, if you think the kind of mixed composition, which is going to have the binder as well as the aggregate property together, is going to provide the sufficient strength. Of course, the mix design is very important, but we are going to talk about that how the mix design is now being converted into the different domain altogether actually. So if you see nowadays, a lot of development is happening in terms of recycled materials. You have the different binders, you have different additives. Some people are adding fiber, so waste plastic, rejuvenator, biobinder, all kind of things are coming up. How do you really understand? How do I find out the strength of the mix, which is going to be laid down on the field? What is the simple tool that we can develop to understand the shear strength behavior or the characteristics of the mix actually? You see, these are the typical photographs, and you can see how severe these distresses are on these particular highways. In fact, even after milling, we can see this kind of distresses are coming up. This is completely, you see, the secondary consolidation, or the mix is not at all in the shear strength, which is simply going or heaving on the either side of the wheel path actually. And these are the very serious issues. Many places in India, you can see these kind of issues are coming up now actually. You can also see the cracking, but we have not seen many pavement which is failing in cracking right now. But yes, you can see the cracking. Sometimes we have seen the cracking coming from the top. So we see the top down cracking is coming up, but at some places we find we design the pavement in terms of the bottom up cracking. So we see the top down cracking and bottom up cracking. So these are the two issues that people are really trying to find the answer, that how do I balance these things together? One side I have the rutting, another side I have the cracking. So something I need to balance, which can I really work out in the field actually. And therefore, if you see the recent focus all over the world, in fact, in US and Europe and other part of the world also, people are talking about the balanced mix design. That what exactly is that? How do I balance the rutting and the fatigue life? My or this presentation is not going to talk about what is balanced mix design. This is going to give you the tool that you can use in the balanced mix design, or you can use a tool which can help you to understand the mix characteristics. But essentially, if you go into the deep of this particular subject, you are trying to balance these two things together. One is your rutting, another is your cracking. And based on this rutting and cracking, you're trying to find out what exactly is the optimum range of the binder which I can use. In India, we have been using volumetric based mix design or the Marshall mix design, and we are not doing any kind of performance test as of now. But yes, I think gradually we have been now like pushing the industry to do some kind of testing on the mixes that we can understand better. If you see this performance space diagram, which is also part of the kind of performance test that we do, one side you have the rutting test, other side you have the cracking test. And based on the threshold value, there is again, like the kind of debate, or you can say the confidence level. How do I set up the limit? So I have set up the limit here, let's say 80, for example. My CT index has to be more than 80 actually. Or my rut depth has to be less than, let's say 12.5. For example, it's less than 12.5, or the CT index has to be more than 80. And based on that, you may also do the field validation, because right now a lot of work is going on. How do I validate those simple performance tool that people are using into the field? So you can draw this phase diagram, and based on this phase diagram, you can understand what kind of mix do you have, what kind of mix are you designing. For example, if suppose your mix is having rutting more than 12.5 or whatever the threshold value, or cracking is also less than 80, so definitely this is the poor mix, which is the poor rutting as well as cracking performance. If you have this kind of mix, which is having very high rutting, but cracking is okay, it means this is the soft mix. And if you have rutting is okay, but cracking is very poor, it means this is a stiffer mix. People are trying to go here actually. But remember, this going here is okay, but you also need to understand that the cost economics, what kind of cost consideration, what kind of money you are going to put up to move your mix from here to there, from here to here, or here to there actually. So those kind of things are now people are talking about, that what kind of changes we have to do just to make sure that we have the good mix which we can lay down in the field actually. Now the things comes or the focus of this presentation is rutting, and we are going to talk about what tools are there in the literature or in the industry, what kind of experiment or what kind of testing people are doing. And if you see these particular photographs, which is taken from one of the highways, how this particular setting has come up on this particular film, and that this is the wheel path here. You can see the wheel path, the complete consolidation is there. However, if you see the second layer, it looks quite intact. There is no secondary consolidation in this particular layer, but yes, the top layer has gone under considerable consolidation actually. So how do I understand that? What kind of tools that I have which I can really utilize during mix design, or maybe the quality control or quality assurance stage? If you see, this is the phenomena that how the rutting happens, and these are another photographs from one of the highways. You see how the rutting is happening. So you have the initial primary stage, then you have the secondary stage, then you go for the tertiary stage. And once your mix reaches on this stage, of course, it's very difficult to control it actually. It will keep on deforming, keep on filling in the shear, and then eventually you are going to see that the whole system is getting failed actually. So that you need to really control somehow at some stage, either not only the mix design, but yes, the paving practices are also quite important actually. So these are the tools that we have right now. In fact, when we do the mix design, And after the mix design, you just find out what is the like the Rutting characteristics of the mix, what is the Hamburg wheel tracking we use, or maybe APA, or maybe the flow number. So these are the like the widely used test methods right now. And I will discuss this particular test in the detail later on. But this is the Hamburg wheel tracking. The cost of the instrument can be quite significant. And if you see the preparation of the sample, compaction of the sample, and then testing, and then you cannot use this tool on every day actually, because it has to be used maybe, let's say, during mix design. But during QC, it is very difficult because during the production, you have to do the sampling, then compaction, then wait for a couple of days, or maybe the quality assurance stage, you have to do certain kind of like homework on that actually. Definitely the flow number is again a very sophisticated test and not easy or not really straightforward. You have to do a lot of homework. You have to compact the sample, pour the sample, then do the testing, then come up with the results. But yes, I think this is the dynamics testing that you have, and this is the torture test. You can say the Hamburg wheel tracking. And some part of the, in fact, in many DOTs we also use APA, which is also similar to Hamburg wheel tracking, but the conditions are different. How do you compact or how do you apply the load actually on that? And if you see, I will just briefly discuss about Hamburg wheel tracking because there are many attendees maybe there who don't know what exactly the Hamburg wheel tracking and how do we use it. And this is the photograph from our lab. This is the Hamburg wheel tracking test. And usually we compact the sample at 7 plus minus 0.5% air void, which indicate the field conditions. And test temperature we can change. Maybe you can make it 50 degree, 55, 60 degree, whatever the test temperature you want. And then these are steel wheels. We have the rubber wheel as well, but we are using those steel wheels right now. And this is how the sample looks like. And this particular sample, and then we will travel back and forth. It will go maybe, let's say, 20,000 passes. If you want more, it can go more as well, actually. So once the testing is done, you see what kind of rutting is coming up, whether it is within the threshold limit or not, actually. But yes, I think this is require a lot of homework, a lot of expenses to be done, and also the manpower is to be skilled to run this particular test. Similarly, flow number. Again, same way you can, but this is the dynamic loading condition. You apply the cyclic load here actually. You apply the cyclic load with certain frequency and you run the test. And after the running the test, you find out what is the flow number. Remember the word I'm using here, the flow number. So flow number is very important because the flow number is going to indicate higher the flow number, better is the mix. That's how we think about. But rarely I have seen industries running this flow number test because it requires a lot of compaction, cutting, coring, then again working in the lab, then bringing it back to the instrument. So a lot of homework is required to conduct this particular test. So these are the limitations. Of course, you require expensive instruments. You require saw cutter, you require sword cutter. So these are the additional expenses that you have to incur. And of course, this is not possible for the industry or for the contractor to have all this kind of setup in the lab, in the field. It's sometimes impossible to have everything actually. They may have sample tool, but they may not have everything in that actually, and they cannot really run all these tests actually. Not also feasible actually to run all these tests. So now what is happening if you see the balance mix design as well as the simple performance tool, and people are talking about actually. What is a simple tool that we can really develop to understand the rating difference? And if you see the simple performance tool, people have come up with the simple definition. For example, it should be simple. It should be doesn't require a lot of complicated instruments or machineries, no cutting, all kind of thing. Or it is easy to use for the quality control and quality assurance purpose. So it has to have good correlation with the existing test methods. It should be good to use as a quality control tool or quality assurance tool, or it should be simple. It should not require any complicated setup. Whatever setup contractor has in the field, can we use those setup to understand the behavior of the mix actually? Remember, we are talking about a kind of index number. This is pass or fail, whether this mix is good or bad. some kind of threshold or some kind of tool that we have to have in our hand to understand the mix is good or bad. If you go through the literature, and there are a lot of literature available right now, and Marshall stability, this is a part of Marshall-Mix design. In India, we are using Marshall-Mix design, and the Marshall stability is done. And this is another very important test which many DOTs are using. In fact, this is high temperature IDT. So you are doing IDT, but temperature is increased actually. Let's say 50 degrees Celsius. You are running IDT at high temperature. And this is another one of the simple tools that is there as a part of the balanced mix design. You have ideal RT also, which is another tool that some of the agencies are using. Again, there is a different jig. I will talk about that later on. The temperature is 50 degrees Celsius. You may have other simple tests also, but yes, they require different kind of setups. But widely, you are going to see high temperature IDT as well as ideal RT are the widely used test method. Right now, the industry is really putting a lot of focus on that actually. And the loading conditions and what are the air voids and what kind of like aggregate sizes, the sample sizes, all these things you can see in the literature. So if you see this ideal RT, now I'm just going to start slowly on what exactly we have done. This is the ideal RT test. And if you see the jig here, and if you see this is the jig of ideal RT, and this is the sample which is rested here, and you are applying the bar which you are applying the load from the test like this. You see this very interesting setup which is developed actually. And if you really think in a very simple way, let's say for example, I assume simply supported on both sides, and I'm applying the load from here actually somehow like this. Very simple kind of really this kind of phenomenon, but yes, I think this is going close to that actually. But remember here, there is a no confinement in the bottom. In the bottom, this is open actually. So this is once you apply the load, this particular in the bottom there is no kind of support, or there is no confinement in the bottom. But this is how the ideal RT setup is being developed. And in this particular setup, you have the dimension of the sample. You have typical air weight, which is 10% plus minus 1 or plus minus 0.5. You have the temperature, and loading rate is same as Marshall stability or whatever the test we typically do on the machine. Very simple test. You don't require any cutting, no notching, nothing actually. You just compact the sample, put in the jig, do the testing, and you get some value out of that actually. What is that value? What kind of sense it is going to give? We are going to talk about that. So this is ideal RT. Remember the setup that I'm talking about. Simple tool. There is no confinement in the bottom, and you apply the load actually. And if you see what usually we get from this particular test, and this particular test, you apply the load. Once you apply the load, you have the deformation as well as the load. This is the kind of data that you record from the machine. You have the displacement and you have the load. And you have the feed load here at what load the mix is getting filled. And once you have these values with you, and if you see how the sample is getting filled actually, how the sample is getting filled in this ideal RT sample. Remember the feature that how this sample is getting failed, because later on I will show you that how sample fails in other kind of test actually. And based on these values, whatever the maximum load that you have, you can find out the shear strength. And what we are using right now is the RT index. Remember this value that I'm writing here, RT index. And this is some value has been established in the literature that what has to be the value of the RT index, whether it is 70, whether it is 80, whether it has to be 100. How do I really define the threshold value actually? So that those kind of debate is going on now actually. What kind of threshold value, what kind of traffic loading conditions, how do I change it? All these things are right now going on actually. And if you see the high temperature IDT, it is same as indirect tensile strength. And if you see the setup here, this particular sample here, and there is a strip and one more strip on the top, and you're applying the load here. Remember in the ideal RT, there was some confinement at least on the both sides, but here there is no confinement at all. It's simply applying the load from the both sides, and then the sample is getting filled like this. And this test is quite popular. We usually do this particular test for tensile strength ratio. Those who are familiar with this particular terms actually. So, but the only change that has been done is the temperature. Otherwise, we have not changed anything in this particular setup. We are using same formula, same loading conditions, same air voids. Only the thing is the temperature is changed actually. So if you see the typical ITS of the mix can go maybe 1.2, 1.5 MPa, but in this particular situation, the value may come down actually because the temperature has increased. So remember two tests I'm talking about: ideal RT, and then this is the HTID. So these are two simple tests I'm talking about right now actually. Now, what is happening in India? Now I will tell you the motivation, what we have done and why we have done actually. So in India right now, we are using Marshall McGee design. So this is how the Marshall setup look like. And you're going to see this setup almost in all the labs actually, everywhere, mostly in all the labs in India, all the contracted, they do have this setup. And this is the compactors that you can see, and this is the samples, Marshall compacted samples, and this is the setup. You see, very interestingly, this setup has very unique kind of jig actually that you have to pay attention. This has the confinement in the bottom, and also this has the confinement on the top. And there is a little bit unconfinement because, like when you apply the load, that it has to come down. But you can say it is like, like almost like close to confinement stage, it is there. And when you apply the load, you get the Marshall stability. And if you go back to ideal RT, which was not having confinement in the bottom, and STIDT, which was not having confinement at all. Now, what we thought about that, why don't we think something different out of this actually? So this is the confinement here in the Marshall. This is the confinement in the Marshall here. And this tool or this particular jig is available almost in all the labs. Very simple to do because anyhow we have to do it as a part of the Marshall McGee design. So we thought, how do we apply this jig? Can we do some modification on this jig itself and use it actually as it is without doing any kind of fabrication or ideal RT or something like that? And this is what we thought about. This is ideal RT. You see the jig, pay the attention on the jig here. Pay the attention on the jig here. This is the loading condition. This is how the load is coming up. And this is the Marshall stability. Now, what we have done some combination here and there actually. And you will see what combination we have done and why we have done that and what exactly is coming up. You say, pay attention here. Say, this is Marshall. You have confinement here. You see ideal, you see high temperature IDT. And what we have done, we have combined them together actually. What we have done, we have removed this top cover out of this particular Marshall stability. And we have kept this particular confinement and we have kept this IDT tip here. So reason we wanted to do, we wanted to provide some kind of stability on the bottom, that the confinement shape, that how this sample is confined, because when you put the top layer, the BC layer, that the below layer is there, the intermediate layer is there, the base layer is there. So we wanted to provide that kind of support and then use this particular space to apply the load and then see how the result comes up. And right now we are working on the kind of modelings and all, but it was very straightforward kind of thought process that let's see how it comes actually. And whether we have some kind of correlation with the existing methods or RT or any other test actually. So that was the simple concept, considering the field applications or the kind of work that we have in India. And this is the failure pattern. If you see the ideal RT, which is already being used, you see this is how the pattern is coming up. And if you see this particular tool, or we are calling it Marshall RT, we did not give it a unique name or different name because we thought, I think this is part of the Marshall, and then we just somehow did some here and there, some changes. And again, you see the stress condition is like this. And if you see there is a shape change slightly because it is supported on the bottom actually. And if you see the Marshall stability, there is no failure at all. Usually sample is squeezed in the Marshall stability. So you don't really see the behavior or the shear behavior in the Marshall stability. But in this particular two test, definitely there is something which is going on actually. You can see certain kind of failure pattern, which is as close to the field which you see for the shear failure. What we have done in this particular study, we have collected 9 different mixes, and these all are by the way plant-based mixes. These all are field mixes actually. We have collected in different part of the India. We have collected the mix, and if you see the mix here, this is 13.2, which is close to 12.5, which is used in many of the DOTs. Then we have 19 mm. We have, this is the base force, which is larger aggregate. PMB is the polymer modified binder. CRM is the chrome rubber modified binder. And this is your unmodified binder, which is VG40. You can little bit sense it close to AC40, but not is viscosity grade actually, unmodified binder. Because they are the base coat, they are the larger aggregate, we are using unmodified binder in that. So we collected 9 different asphalt mixes from the plant. And those highways where we collected these mixes, they were having traffic more than 30 MSA. When I'm saying more than 30 MSA, some of the highways have traffic more than 30 million standard axles. So MSA is same as million e-cells actually. That is, so they may have traffic as high as 100 million standard axles or 100 e-cells, million e-cells actually. All these mixes were designed using Marshall mix design. All the mixes satisfy the volumetric stability requirement. So volumetrics was absolutely okay, no problem at all. Stability was absolutely fine. All mixes were designed using the Marshall stability. We wanted to see how these mixes are going to work out. If we put these mixes in ideal RT or flow number or Hamburg or Marshall RT, how they are going to behave actually, and what kind of traffic conditions they are going to satisfy. That was the purpose of doing all this exercise. And that way we were getting some kind of insight into the new test that we tried to explore. So first what we have done the Marshall RT. We compacted the sample, and for all 9 mixes, typically we have done almost 4 samples for each mix for Marshall RT. And airwood we have kept around 7 plus minus 0.5. Temperature is 50 degrees Celsius, and this is how the setup look like. And if you see this, what exactly we are doing, how we are doing the calculation, that is also important. We are not using the peak load directly. We are also doing some certain kind of what is work done actually before failures. So we are dividing into 3 different zones. One zone is the peak load. You see the peak load here. This is the damage-free zone, and there is a damage starts in this particular zone, and then this is the failure, the cracking. What we are doing, we are taking the work done before it starts initiating the failure actually. So this work done can be calculated. So we are using 2 parameters here. One is the peak load, another is the work done. So please remember those 2 values that I'm talking about. One is your peak load here, another is your work done for the deformation damage. So 2 parameters we are trying to see how they are going to correlate actually. And this is how the interesting result look like. If you see all these 9 mixes, remember this G, H, and I, they are the larger size aggregates. You can see the larger size aggregate here. And A is your modified binders. Some of the mixes shows very, very less peak values. For example, if you see mix number C, it will show 2.3 kilonewton. And this Pmax is coming from Marshall RT test like this, with the peak value that's aggregate. If you see the larger size aggregate, of course, it is showing very, very high the failures in the Marshall RT 9.4. And if you see the work done also is very high. So this is how the different category look like. But how do I really categorize them based on different traffic conditions? Of course, I can have from this particular diagram, you can see this mix is not working out very good, or this mix is not working out very good. But we need to correlate that. Remember, this is the new test that is coming up. So we wanted to correlate that what kind of correlations are going to come up from flow number, from Hamburg wheel tracking, or from ideal RT. So we conducted Marshall RT, and then we correlated this particular outcome with Hamburg, then flow number, then ideal RT. And let's see how the number look like based on this. And Hamburg wheel tracking also, the testing was done. And you can see all different mixes. And this is your rut depth. These are all the rut depth you can see here for all the mixes. Some of the mixes failed prematurely also. So these are the rut depth. And you can see the RRI value, which is going to normalize the rut depth because some of the mixes fails pretty earlier. So RRI value is also being calculated. So this is how the mix look like. And if you see from here, red depth is quite high for some of the mixes. And red depth is quite low for this particular mix because this is the larger size aggregate that you have. Now, this is quite interesting because if suppose this particular red depth or RRI value correlate with the Marshall RT, then we can have certain confidence on this particular setup that we are developing. And therefore, later on, we have correlated that actually. We have done the flow number also. And flow number, if you see, the flow number of the larger size aggregate is quite high. There is a high variability also that you can see here in some of the samples. And if you see the mix number C, remember I told you in the beginning that all the mixes were collected where the traffic was more than 30 MSA, million standard axis, more than that. But this particular mix is really showing, like a very low flow number. And if you go to the literature, for example, one of the literature, they talk about that flow number and what should be the flow number and what should be the traffic. It means if your flow number is more than 415, the mix may be suitable for 100 million standard axles. If it is less than 15, then definitely it is 3 million standard axles. Likewise, if you see NCHRP also, they also talked about the flow number versus the traffic. And this is quite interesting work. A lot of work has been done in NCHRP. They have done extensive work to establish this kind of range. And that was the clue for us that how do I establish the different RT values or Marshall RT values for different traffic loading conditions. And this is what we have done later on actually. And this is ideal RT also. Remember in ideal RTs, some of the, in fact, agencies, they're using 90 RT index, some of them they're using 80, some of them they're using 100. So if you see maybe 90 or so, then this is how it will look like. So some of the mixes are really failed. For example, this mix is failed. And some of the mixes are really satisfying the minimum threshold values. Now, remember this, again, a lot of work is going on in the industry that how do I really validate those ranges in the field actually. If you see the variability, this is quite interesting because as I told you that the flow number, the variability is quite high. Sometimes you test maybe 3 samples, 4 samples, 5 samples, maybe sometimes you have to test maybe 5, 6 to a lot of samples just to minimize the variability. And remember, doing the flow number is not really a fun task actually. You have to do a lot of homework, cutting, coding, then again doing the testing, then coming back. And if you see this kind of variability into the test method, then definitely the credibility goes down actually. Yeah. And if you see the Hamburg wheel tracking also is very high variability. We have seen some of the samples fails prematurely and some of the samples sometimes take a lot of number of cycles. Definitely you have to increase the number of replicates. Ideal IT also typically 20% or so, ranges from number of samples that you have been doing. And Marshall RT, this is Marshall RT. If you are seeing here, this is also showing like variability less than 20% that you can think about actually. So what we have done, this is what we have done. We have compared flow number versus P max. Remember the P max is coming Marshall RT. When we are doing the Marshall RT test like this, that the maximum load came up. This is the displacement, this is the load, and this maximum load is coming from the Marshall RT test. And flow number is there. This is the flow number, and this is your P max. And we have trying to see the correlation between these two, whether the flow number is really getting correlated with the Marshall or the Marshall RT or not. And it looks like very reasonable correlation between these two. Definitely, there is a number of mixes are quite less than 9, but yes, we are keep on adding the number of mixes now. Right now, we may have more than 20 or 30 mixes that we are going to plot. But yes, it gives some indication that yes, I think there is something, some correlation is there between these two tests, and this Marshall RT can be utilized later on actually. Likewise, if you see Hamburg wheel tracking versus this Max, again we see certain kind of variability here and there, like a couple of mixes that looks to be outlier. But if you go for the 95% confidence band, it looks to be fair correlation between Hamburg wheel tracking versus the maximum load. If you go for the ideal RT, and remember the ideal RT is again widely used as a simple tool versus the P max, which you are getting from the Marshall RT, we are getting very beautiful correlation between these two parameters, which gives a lot of confidence that yes, I think this is another tool which can be used for understanding the rutting resistance or the shear behavior or the kind of screening tool that you can think about actually. Same thing we have done correlation with the work done. What was the work done? Remember the work done was like this. You do the Marshall RT, and then this is the work done. This is the delta, this is the load here, this is what. And we got very good correlation with what kind of work done versus flow number, then Hamburg, then ideal RT. So this also gives some confidence that yes, I think this test we can further explore this test to understand the behavior of the mixes. Now this is the interesting slide. I have 2 or 3 more slides and I'm almost done. Remember from the literature, we have taken some limits, the traffic here, and this is the flow number. If you see for 3 million e-cells, the flow number has to 15. What we have done, if you see these back slides, what we have done here for 100 MSA, for example, this value is 415, and this is for 100 million e-cells. So for 100 million e-cells, what is the max value that we require? Like this. And for minimum, likewise, for 100 MSA or 100 million standard Excel, if I'm considering this as a limit, what is the value that you need? Likewise, for RT, that I'm assuming close to 90. For 90, what is the maximum value that you need? So that kind of correlation we have developed actually. And this is for the different traffic loading condition, 300, 30, and 100 MSA. And if you do the correlation, an ideal RT comes close to 90 if your traffic is more than 100 billion standard axles. And remember, which is the value typically agencies are using, close to 80 to 90. And if you link this back to Marshall RT, maybe the maximum load, which is coming around 5 kilonewton, if you go for the work done, which is close to 14 kilonewton mm. If you go for 30 MSA or 13 million e-cells, then definitely this value comes to 2.7 or 6. And likewise, if you use LCH-RP threshold values, again, you can find out what are the different threshold value of the T max as well as the work done for mass test. And likewise, you can also develop different threshold value for the ideal RT. Remember, this has to validate it. You're just putting a lot of emphasize on these values are logical, and therefore other ranges are also logical. So this has to be validated, whatever we have been putting up here actually. So finally, what we have done, whatever the mixes we have collected, remember in the beginning I said 9 mixes we collected, and these are surface mixes, these are the binder force, and these are the base case. And PMB mix here, if I categorize this particular mix, and also I mentioned that we collected the mix where the traffic was more than 30 MSA, or maybe sometimes more than 50 MSA, but let's assume more than 30 MSA. All these mixes are absolutely okay if your traffic is 3 million e-cells, or in India we call it million standard axles. But if you increase the traffic level, for example, if I go for the 30 million standard axles or 30 million e-cells, then definitely you see the Dharamveer is not working out. And this particular mix is also not working out. There is some issue with that. But if you further go up, for example, 100 or maybe more than that, then definitely you see that these particular mixes are not really working out for these heavy loading conditions. And all these things are ranked based on the Marshall RT that we have done. And right now, what we have been doing, wherever these mixes have been laid down in the field, we have been monitoring the performance of these mixes, how these mixes are going to behave in the field, so that we can have some sense on this particular test that we have developed. So finally, this is the last slide. And I would also encourage that you also try to generate some data out of this test. Very simple tool. You just pick out this upper Marshall jig, keep this one, apply the bar, and this is how your YouTube becomes up, and get out some value out of this and try to see how the things look like. You can design for different sample size also, whether it is 4-inch or 6-inch, different type of the mixes, RAP or WMA or whatever you want to do it and think about. So this work has been published, as I informed you, in IGPE last year. So you may go through the paper and then see the kind of lot of interesting data analysis that we have done in that particular paper. And with that, I would like to thank, and this is thanks to Dr. Jaman, who stayed us in March 2019. And thanks to all those who had attended this particular webinar. Thank you, Michael.
Excellent. Thank you so much, Dr. Singh. That was a great presentation and right on time too. So very well done. We do have a few questions now from posted in the chat. I'm going to read those out. And while I do, please go ahead. And if you're in the audience, if you have other questions you'd like to ask, you can post them in the chat or raise your hand and we can get to you after these. So first question we have from Dr. Zaman. He asks, how do you include temperature effects in determining shear strength parameters for asphalt mixes?
That is quite interesting question, actually. So what we have done a lot of literature review. And in fact, in Indian conditions, we have been seeing what is the pavement temperature look like. And typically temperature goes 40 to 60 degrees Celsius. And we wanted to select one temperature which is already being used for other simple test so that we can have certain correlation actually. Yeah. But yes, certain temperature is to be selected, but you cannot also select very high temperature, otherwise testing will not be able to, you will not be able to do the testing. It will collapse.
Great. We have one more question. Is moisture damage a major problem in India? How is it handled in designing asphalt mixes?
Yes, I think it's not really the major problem. But yes, we do this tensile strength ratio, TSR, the moisture conditioning, and then we find out dry ITS and wet ITS, and then we try to find out the ratio. But we have not seen major problem as far as the major highways are there.
Looks like we have another question in the chat from Montoya. When correlating data, what interpretation should be given to the confidence bands?
Yeah, I think that's good point actually. So our main intention was we wanted to see whether the kind of parameters that we're getting from Marshall RT, they are having certain correlation or not with the ideal RT or flow number or something. So what the confidence we got that yes, I think this particular tool can be used, and you can definitely have certain kind of confidence on the mixer that you are developing. But yes, validation is required. Once you do the validation, once you design a mix, do this particular test, and then monitor the field performance. Yeah.
Great. Thank you for the question, Miguel. And from Ken Hobson, I like the correlation of WMAX versus rutting and FN rather than total work used in some other methods. Right. And Dr. Zaman, I see your hand.
Yeah, thank you, Ken. Yeah.
Yeah, Dharamveer, this is really wonderful work. I think, simplicity is extremely important, and I particularly like the fact that you are trying to look at what the industry can use in practice, in quality control and quality assurance. So I think this is really important. So I think and you did not talk about the balanced mix design per se,
right.
But
right.
of course, the other side of this is the cracking. So
right.
I think so. In India, if you look at it, most of your roads, which is the more, because somehow I think we get the notion in this country, and Ken, you correct me because Ken has a ton of experience.
Yes.
So we kind of give the impression that we have taken care of rutting problems. I think it could be a totally wrong notion, but that's how we would like to think, or we're we are portraying. So in India, if you compare those two,
right.
Could you kind of give some
Yes.
overall picture as to what is most important in designing asphalt mixes in India if you take the cracking also into account?
Yes. So thank you very much, Dr. Jaman and Ken as well. In India, we are designing the mix based on the Marshall mix design. And what we are seeing right now, a lot of failures because of the rutting is happening prematurely also, and after a couple of maybe a few years. And cracking, we have not seen really on a kind of large scale. But yes, at some places. But I would, if you ask me to rank, like rutting is first, then goes to the cracking, and or maybe the moisture is almost same actually. Yeah. So the rutting is the major issue. And the reason is because we are not designing the kind of mixes based on the traffic or climatic conditions. Sometimes the same mix design or same tools has been used wherever we want actually. So I think rutting is the major issue that we have been facing right now actually. I remember Dr. Jaman when this Marshall mix design was there in US, and then they switched over to SuperPave. And that was the major concern, that what changes has to be brought into the aggregate gradation, what kind of changes is to be brought into the SuperPave PG. Exactly the similar kind of things is happening now actually in India. We have been really slowly shifting actually. Yeah.
Absolutely, and some of the things coming back also. Dharamveer, I
Yes,
think maybe
agree.
Ken can actually
Right,
shed some light because he played a key role in actually making this switch.
right.
To yeah. So anyway, but I'm really impressed with the work, and I also particularly like the different variations. One of the things that we normally not do
Mhm.
often is to compare different test methods, right? We are
Right,
not really, because material is material and it will behave the way it is supposed to. We
right.
can also modify, as in engineering. That's one of the things we do. But I think in your case, you have really taken different test methods to look into
Mhm.
the same problem. Writing is your problem, but you're looking at really different test methods objectively. I think
Right,
this is the type of thing people need to do instead of being biased to one method or the other. And the other part
right.
I also like, that bringing the mechanistic part. You're not randomly correlating. You're saying that this should correlate because. So
Yes.
I think this is the work done and the peak load, energy, all of those things make sense because those are really important to material performance, material behavior. Wonderful work, Dharamveer. We really, really appreciate your presentation here. And the people who could not attend, they will have access to your video as well as they will have access to the slides.
Thank you, Dr. Jaman. I think, yeah, I think the whole idea came from industry because they, they cannot spend money every day actually, and doing hamburg wheel tracking, doing flow numbers. So they want simple test. And what simple, depending upon the conditions, that's what we're trying to look into that actually. So thank you very much for your motivation and encouragement.
All right, we have a few more questions posted in the chat. One is PMB the best choice over CRMB depending on Indian job site conditions?
Yeah, I think, Michael, these questions are coming from India, looks like, because these terms are quite familiar. PMB and CRMB, we have seen the mixed, by the way, PMB means the polymer modified binders, which is polymer modified asphalt in US, and CRMB is rubber modified asphalt binder. And we have seen mixed behavior of these two kind of binders, depending upon the traffic condition, depending upon the pavement design also actually. So I cannot say this is good, this is bad. It all depends upon how do you design the pavement, how do you really put up your mix into the field.
Right. Next question is there any modeling done to see how the Marshall RT failure pattern matches with filed failure?
Very good point, actually. This is excellent point, and this is what exactly we have been doing. Vamsi, who is here, and when somebody is going to ask a difficult question, I will ask Vamsi to interact. So Vamsi, you can share some light on that. If you allow, Michael, Vamsi, who is my PhD student, who is working on this particular project. So he's working on the modeling right now, actually.
Sure. Yeah, he should be free to unmute.
Yeah.
Yeah, thank you for the question. Yeah, we are working on this modeling and the mechanical analysis and the analytical solution part.
Yeah.
So once we are done with that, and we'll happy to share the result.
Right.
All right. I see someone's hand up. We'll get through a couple more questions in the chat, and then we'll go to the person who has their hand up. Next question, is there any reason that in ideal RT support at the bottom is not there?
I think that's an interesting question. What I see, I think possibly they wanted to design as a simply supported, as I initially said. But yes, I think I don't see any specific reason because we have seen the modeling also. But that is also quite interesting test, by the way, because it gives good, interesting outcomes. But that was the clue we got that why don't we provide the support actually in the bottom and see what is coming up. So maybe Dr. Like Zhao from Texas TTI, he can answer better because they have developed the test. Yeah.
Right, great. Next question. If other modeling is done, can you share the results?
Yeah, I think it will be published. We're publishing all of our work in the very good international journals, so you can always access that. You can go through our websites and all. Yeah.
Okay. The next question is the ideal RT and ideal CT the same test?
Not really. CT is the cracking and RT is the rutting, so both are different. Yeah. Test not only the procedure, but the analysis and the tools and jigs all are different.
All right, and I see an individual with their hand up, CB Raman. You can unmute and ask your question if you'd like.
Mm-hmm.
I still see you muted. You should be able to unmute. If not, you can type your question in the chat.
Yeah, I see one more question.
Yeah, thank you, Dr. Dharamveer sir. You have given me opportunity to join this session, and really it is very informative, and really it's the kind of test you are suggesting. Definitely, as EPC contractor and as authority engineer, we would like to implement here to get some better result. My question was related to the kind of modified bitumen in the form of CRMB and PMB. You have suggested the VG41 is better one, all of among three. So further the modification in the gradations like use of the micro silica or something can be added with the VG40, and do you have some data related to that for the further modification? Because the kind of finers we are using into the bitumen, I think the rutting possibility can also be minimized by making it the composition with the kind of filler which we are adding with the bitumen. So have you any kind of test conducted with you where micro silica as a filler you have used with the bitumen as a filler?
Yeah, I think thank you, Ramanji. I think this is a good question. People are trying different kind of fillers, industry fillers into the bitumen mixes, and they have been seeing promising results, by the way. But application, how do you inject into the plant? That is kind of something which we need to pay attention. We need to require certain setup. But yes, this may have certain benefit, but we need to explore into that. And you will find a lot of literature to see different kind of fillers that people have tried actually. Not in the bitumen, but they have tried to put in the aggregate directly actually.
Yeah, because micro silica can be added with also. Right. That is micro silica or nano silica, whatever things.
Right.
All right, we have one more in the chat and then one with their hand raised. We'll do the chat first. Ken asks, would you eliminate Marshall stability test and substitute Marshall RT, or does Marshall stability hold value for other reasons besides mixed stability and rutting performance?
This is a very intelligent question. I would say, Ken, I think good. Thanks for asking this. And we were also curious on that. In fact, I did not show you the results, but what we have done, we have correlated Marshall stability with flow number, Hamburg, Marshall RT, ideal RT. And unfortunately, we did not see any correlation actually with the Marshall stability. So to answer your questions, Marshall stability, if you can replace it with Marshall RT, it will be much, much better. So we have done that actually. I could not show that, but we have done that. Yeah.
Okay, we had one other individual with their hand up. You can unmute and ask your question or type it into the chat. Yep, I still see you muted. All right. While we wait for them to get unmuted, we have one more in the chat. What is the test done for both rutting and cracking finding in a single test for better result?
Single test cannot be done because the test temperatures are different for cracking and rutting. And so we have not seen any single test which can do kind of give the indication for both kind of performance. So that's not possible as of now. But yes, I think we'll think about that. Yeah.
All right, that's all. And that's all in the chat. We do have one person with their hand up. You can unmute yourself if you're able to. Right. Well, yeah, if you're not able to ask your question, I think, is it okay if people email you with questions afterwards?
That's fine. Absolutely okay. No issue.
Okay, perfect.
Yeah.
All right. It doesn't look like, oh, wait, I see the mic on. Yeah, did you want to ask your question? Okay, I'm not hearing anything. Right. Well, it looks like if you would like, you can email Dr. Singh with your question later if the mic isn't working. Yeah, I just want to conclude and just thank everyone for attending. And first of all, thank Dr. Singh for this great presentation. As a reminder, as Dr. Zaman mentioned, this is recorded and will be posted online on our website along with the presentation slides. So please give a round of virtual applause for Dr. Singh. We will be sending out a survey afterwards. So please provide your comments on this webinar and suggest topics you would like to see in the future. And professional development hours will be sent out to those who need them. So thank you, everyone, so much. This has been a real pleasure. And thanks again to Dr. Singh for this wonderful presentation.
Yeah, thank you. Thank you very much, Dr. Jaman, Michael, and SPTC. And thank you very much to all my students and also many known faces who have joined and supported me and they are listening. I'm thankful to all of you for joining and then showing their strength.
Thank you, Dharamveer.
Thank you.
Thank you.
Goodbye.
Thank you, Dr. Jaman. Have a good day. Please take care of yourself. Yeah.
You too.
Thank
Thank you, Ken. I could not hear Ken. I wanted to hear his voice.
Yeah.
Yeah, I'm just.
I think he left. Ken, can you show me your face? I need to see you because I did not see you for long. Yeah. How are you? Good to see you. Good to see you. Yes.
Yeah, Ken is still actually our heart of our lab.
Oh yeah,
Dharamveer.
I cannot forget his support actually that we
Yeah,
used to receive.
absolutely.
But not possible.
And the level of knowledge he has is
Yes.
really deep, very deep, and I think he
Very deep.
continues to be a major force.
Agree.
Also, another person that I think kind of really maybe future Dharamveer, Ashik, can you turn on your
Ashik, where is Ashik? Yeah.
Ashik, turn on your camera if you can. So, that's one of the reason I think, we have really number of people, like you, Rafi, and other people who graduated from our program. I think this is really, I think you all are ambassadors and a wonderful one. Ashik, is your camera working, Ashik, or not working? So maybe he may have signed off. I don't know.
Oh, he has an issue with his camera.
Yeah, he has some issue with his camera. So, Dharamveer, I think the other thing I'm really impressed that the graduates that you're producing, their publication is phenomenal. I think that's wonderful. That shows your leadership, that shows your skills actually in raising and grooming these people. I think that's how we survive, generational shift. So we appreciate everything that you're doing, Dharamveer. Please give my regards to all of your colleagues, and we hope that you visit us soon.
Yeah, I think Dr. Jaman is your training that has made us so strong. I mean, it was hard training. It was good training.
We all learn from each other, right? So,
yeah. Thank you very much.
Yeah, thank you. And thanks, Michael. You have done a wonderful job in moderating this session.
Yes, thank you, Michael. Appreciate it. And all the staff of SPTC. Definitely,
Absolutely.
It was quite long pending, but finally we could make it. Thank you very much.
And all the audiences. I think we had large number of people attended.
Yes.
108 or 10 or so people. I think that's wonderful. Thank you again. We'll talk to you then a bit.
I'm leaving right now. Yeah.
Thank you.
Thank you. Goodbye.
Yeah. Thank you, Michael.
Thank you, sir.